Once we get the idea, it's not too bad, but it'll give me a few moments here. So first, we need some 2D names. So in 2D, anything, and I want to talk a little bit about form. Anything that looks like everything's to the first power is a line, even if it isn't in the y equals mx plus b form. So if everything's to the first power, and this kind of helps set up what we're going to do in 3D. So if you're just given an x and y, they're to the first power, it's a line. If one of them is squared, either this is squared or this is squared, it's a parabola. So for example, 5 plus y squared equals x. So if there's one of them squared, then one of them's not, it's a parabola. This would be like a parabola on its side, but it's still a parabola. So we're just trying to get general shapes. We're trying not to be precise. So 1 squared, parabola. If both are squared, there's a couple possibilities. If both are squared and all the numbers are positive, it's an ellipse. If you happen to have these two numbers are the same, it's a circle. This is a review, but sort of maybe you hadn't thought about it this way. And then lastly, the situation when both are squared, but there's a minus between them. This is probably a shape you haven't worked with that much, but ultimately it's a hyperboloid. And the way you graph it is, and you don't need to be able to graph in this course, is you plot the intercept. So if this is 0, you would say x has to be plus or minus 1. So that gives you 2 points. And then you say, well, what about if x is 0? You get it's not possible because you're going to get a negative. So it turns out you can't have 0. The smallest you can have is 1. It's this shape. You've seen a hyperbola before, but typically it was turned 45 degrees. This thing, 1 over x. Y equals 1 over x is a hyperbola. Okay, so those are the main shapes. So if both are squared and there's one minus, either the x squared or the y squared is minus, then it's a hyperbola. Okay, so because of that, because it's kind of complicated to say, sometimes textbooks like to write it this way. X squared over a squared minus y squared over b squared equals 1. And the reason they write these squares on the bottom is to emphasize, okay, I want those to be positive numbers, to emphasize there's only one minus. But the truth is, that's just a fancy way to say, if there's a minus, hyperbola, if both are positive, ellipse, one is squared, parabola. Okay, that's the 2D version of what we're about to do. So now we're going to move to 3D. So in 3D, you have a few possibilities. One possibility is this. So if someone says x squared plus y squared equals 1, in 2D, that's a circle of radius 1. Here's x, here's y. In 3D, what they're saying is there is no restriction on z, so z can be anything you want, which means you could draw it when z is 0. So that would be like this circle of radius 1 at z equals 0. You could draw at z equals something else, I don't know, 5. So up here you'd have a circle of radius 1 when z is 5. You could draw it at z is 2. You could draw it at z is 3. And if you keep drawing these, you get a whole bunch of circles stacked up. We call that a cylinder. It's basically this extended into 3D. And that's what it means if z can be anything. It's extended in that direction. So technically we use the word cylinder for that. And the word in front of it is whatever the 2D shape is. So you call this a circular cylinder. Now what's new to people is we also use the word cylinder in, I didn't know this till I taught this course, in 3D to describe anything that extends. So if you take, for example, a weird example, here's x, here's z, and you draw the cosine graph, and then you extend it towards us, you're going to get this thing. So this is actually, there's the cosine graph drawn on the xz plane. And since y can be anything, there is no restriction on y, it's extended out this way to get this little wave. So we call that like a cosine cylinder, for lack of a better adjective. There's not like an official adjective, but the word before describes the 2D shape, and cylinder means extended. So that's one special shape that will be easy to identify in the homework. Any question where there's a variable missing, cylinder. Okay, So that's one general shape that's nice to know. Okay, now we're going to talk about situations where all three variables are present. And there's basically a couple flavors, as I mentioned, paraboloids and hyperboloids. Okay, so ultimately there's two types of paraboloids. And again, this seems like a lot, but really it's not. We just need a few shapes. If two of them are squared and there's a plus, so 2 are squared and there's a plus, 2 are squared and there's a minus. This is a hyperbolic paraboloid. This is a circular paraboloid. And you're like, how am I going to ever remember that? Well, you can look it up. You can put on a note sheet. There's a table in the book. But there's an easy way to remember, and it's what we call traces. And the idea is this. So if you were to cover up the x and just look at the rest, really what we're doing is we're replacing x with a number. But let's just for now, we'll talk more about that in detail in chapter 14. Then you see, so when x is fixed, you get a parabola in 2D because one of them is squared. Okay, so then you redo, you erase your thing there, and you say, what if y is fixed? This is a big idea of looking at sort of one variable at a time. You also get a parabola. So somebody said, hey, if in two directions from two sides it looks like a parabola, let's call it a paraboloid. So if two of the traces are parabolas, we call it a paraboloid. And then when you look at z, when z is fixed, so if this was a 1, 2, 3, 4, or 5, it's going to be an ellipse. And that's why we call it an elliptical paraboloid. So this means two of the traces, two of the directions are that. So I have a quick visual for that, but we'll do the next example. When you look at this one, y equals 2x squared. So this has two of them squared. These are all the situations when two of the variables are squared. Two of them are squared, one of them is not. When you go to do the traces, here's what would happen. And what I mean is if you fix x, fix y, and fix z. If you cover it up with your hand. So if you cover up the x and look at the other two, you see a parabola because one of them is squared. If you cover up y and look at the other two, you see a hyperbola. And that's because there's a minus and both are squared. When you cover up z, you see a parabola. Two of the traces are parabolas, so we call it a paraboloid. And the adjective in front of it is the other trace. That's where that comes from. If you look at this, from above it looks like a circle or an ellipse, and from the sides it looks like a parabola. That's what we're actually doing. This one looks like a parabola from this side. It also looks like a parabola from the left, and from above it looks like a hyperbola. That's what we're doing. That's the idea of traces. Okay, so quick example. So if you're looking at this one, and you fix x, I'm going to show a quick visual of this. At any point you can kind of pause and think about it, but I'm trying to do the quick version here. You replace x, you're going to get a parabola. If you replace y with a constant, you're going to get a parabola. This is how I remember the names. I don't ever look in the table. You replace this, it's going to be an ellipse. So I'm just covering them up. Cover up z, it looks like an ellipse. Cover up x, it looks like a parabola. Cover up y, it looks like a parabola. And then the name of it is, to me, it's just much easier to figure that out. So elliptical or elliptic paraboloid. I'm not particular about what that is. Okay, so quick visual on that. I think it's good for us to see this. Kind of, I've been saying. So we're going to look at that example. Here's that example. It looks like a parabola, sort of in all directions. I should change the scale, but we'll just leave it. So here's what we're actually doing when we're fixing x. So when you're fixing x, like here is x equals 0. It's that thing. In fact, let's remove it for a second. It's that parabola. That's called the trace. It's what it looks like if you intersect this surface with this. The key point is it's parabolas. So this is a big thing we'll talk about in chapter 14. But those are the traces. We're just looking at the parabolas that way. And then we switch gears. And we go the other way. And we talk about what happens when you fix y. It's those parabolas. Let's put this back up here. Let's put this up here. So if in two directions it looks like parabolas, we call it a paraboloid. Looks like a parabola from this side, looks like a parabola from this side. And then lastly, from above, let's look at that. Hope these visuals help. Took me a lot of time to make these. From above, it looks like parabola. So that's what we call, or an ellipse in this case, elliptical paraboloid. So hopefully that gives you a sense of what we're trying to do here. Okay, so we've done the case if one variable is missing, cylinder. If two of the variables are squared and one is not, it's paraboloid. And there's two flavors. Okay, lastly is a situation where all three are squared. And if all three are squared, there's a few possibilities. And ultimately, we just have to look at a few. So you have the possibility where all the numbers are positive, in which case we know that one. That's an ellipse. Or a sphere in this case. It's an ellipse if you change one of these numbers. The question is, we don't actually have to look at situations when two of them are negative, and the reason we don't is because you could always multiply by -1 to get this. And if all three were negative, you'd multiply. So we really only have to look at the situation where there is one negative, because you can always make it look like that. So if there's a negative in front of one of the variables, rewrite it so there's only one negative. And then we're going to categorize those. And basically it's going to categorize into three situations. Whether there's a positive number on the right, a negative number on the right, or a 0. And this just has to do with the traces. So ultimately if you did traces, if you picked one of these, all three of these examples I have here, this equals 10. I'm going to rewrite this one here as x squared plus y squared minus z squared equals 0. So I'm rewriting this one. So it just looks like the other ones. And then the last one is x squared. So when you look at these three examples, 1, 2, 3, they look similar. In fact, if you did traces, they have the minuses on a different one. But if you did traces, if you cover up x, it's a hyperbola. Because you have two things that are square and there's a minus. So one of the traces is a hyperbola. If you cover up y, the first one is a circle, but the other two are hyperbolas. If you cover up z, hyperbola, circle, circle. So the traces to this are in two directions it looks like a hyperbola, and from the other direction it's a circle. So we should call it a circular hyperboloid by convention. But it turns out there's a little difference between these. All of these are, so if you look at it from the side, they're hyperbolas. This is hyperbola, it tilts the other way. And if you look at traces from this side, they're also hyperbolas. We'll talk about that picture in a second. Sorry, I should have drawn it like this. So these really are all hyperboloids, but they have special designations. Notice that this one is all connected. Notice that this one kind of looks like it's broken apart into two pieces, and this one's very sharp in the middle. I think of this as the skinniest one. This one actually has a waist, and this one is separated completely. Okay, how do we know when that happens? It has to do with traces. If you look at it from above, they look like circles. The thing is, this one has a skinniest circle. This one has no circle at 0. And one of these three has no circle when you plug in 0. So if you think about it, if you were to plug in a 0 for z, you actually get no possible thing here, because you'd have x squared plus y squared equals -4. So whenever this is a negative, it ends up you don't get any circle there. All right, when it's positive and you put a 0 here, you do get a circle. In fact, that is the radius of that circle is the square root of 10. And when it's 0, you get a very skinny circle, which is just a dot, and we call that a cone. Okay, so in these situations, it's just make it so there's one negative. If the thing on the right is positive, it's a hyperboloid of one sheet. If it's negative, it's a hyperboloid of two sheets. If it's 0, it's a cone. Let's look at a quick example of that. So here's an example from an old test. So if you saw this, you'd go, oh shoot, there's two negatives. You'd multiply everything by -1. all three things are squared. So this is some sort of, it's very important to multiply by -1 because notice it changes this sign. But you go, one thing is negative. If you did traces, you would see hyperbola. That's if you cover up the x, you have a z squared and a y squared and there's a negative. If you cover up the y, you have a z squared and an x squared and one of them's negative, so that's hyperbola. If you cover up the z, you get a circle. And the question you need to ask yourself about the circle is, do you always get a circle? Meaning, if this is 0, does this make sense? And the answer is yes. So that means it's connected. There is a circle at the thinnest piece, but the other way to remember that is this is positive once I got it in the right form. So you could try to name that, but that's a hyperboloid. Again, this tells me that if you ever forget two of the traces. And we call it a hyperboloid of one sheet because there is no break in it. Okay, so a quick couple visuals on that, and then maybe I'll finish here. But a quick couple visuals. This is kind of a fun thing that I just made years ago, that what happens when you have x squared plus y squared minus c squared equals a number, and you play around with whether the number is positive or negative. Let's see if I can zoom in a little bit, just so you can see the equations. Okay, so here's this shape. It's a hyperboloid of two sheets. Notice the k is negative. If you make the k like -1, you get this. If you make the k 0, so the square root of k is the radius of the circle right here. So in this case, it's 1. Then if you make it a little bigger, it's like this. It's kind of like a lava lamp. I always like to watch this. Let's animate it. And while that's happening, maybe we can look at the traces. So notice the traces from the x perspective are hyperbolas. Kind of fun to watch that. Hyperbolas, hyperbolas, hyperbolas. From the y direction, this looks like hyperbolas. So in two directions, it's hyperbolas. So makes sense we call it a hyperboloid. And then from above, it looks like circles. And the question is really, are there circles at 0? And that's what decides. So currently there's no circles at 0 because there's a negative on the right. Eventually you get a cone where there's just a dot. And then after that you get circles. That's why when it's positive, you do get a hyperboloid of one sheet. When it's negative, you get a hyperboloid of two sheets. And when it's 0, you get a cone. So those are just a few named shapes. I know that's a lot of information. There's a few examples in the homework that talk about what if you switch things. Like what if we switch the roles of x and z in this equation. Make this z. It's still going to have the same name. It's just going to change the orientation. So multiply everything by -1 again. But now we have this. The way to think about it is to think about the traces. So in this setting, it was the z-axis when z was fixed, where you had the circles. In this setting, it's the x-axis. So the difference is it's going to be around the x-axis. So it's going to look like this, as opposed to this one, which was around the z-axis. So this is going a little further. We're not going to go into too much depth because in chapter 14 we're going to go into a lot of depth. What happens if we add a 4z? If you add a 4z to the original equation, you might say, well, we didn't study that. Well, you can get around this. Let's write it. I think I intended to add a 4z to the original equation. Sorry, let me write that again. That was the simplified version. Okay, so we're going to add 4z to the original equation. Z squared plus 4z minus 6x squared minus 6y squared equals -9. What happens here is you can complete the square. That's the key idea. So you can add 4 to both sides, half the middle squared, add 4, and then you can write z plus 2 squared. You're not going to do a lot of this. We're just kind of make you aware that, hey, this is the same name. And then you can multiply everything by -1. It's still a hyperboloid of one sheet, but it shifted. It's shifted down 2. So here's a quick visual of those. Let me zoom out a little bit. There we go. So there's the original one right here. Notice that the skinniest part right here, well, because there's a 6 here, you'd have to divide by 6. So if you divided everything by 6, it's like the square root of 1.5. But that wasn't part of my question. If you switch the roles of x and z, instead of it being around the z-axis, the circles are going to look like they're around the x-axis. And then back to the original one. If you add 4z, it's going to shift it down 2. So the skinniest part, instead of it being at 0, it'll be down here at 2. So there's a few little variations on a theme, but that's what that section is. So let's take a peek at the homework. Make sure I'm not lying to you. So here's the homework. It's a lot of questions because it's a lot of naming. But some of these are fast. What is this in 2D? This is kind of the review. Parabola. What does it represent in 3D? Okay, you only have 2 variables. One variable is missing. Cylinder. You don't have to read the rest. What does this represent? Cylinder. So again, if one variable is missing, it's a cylinder. So it should be a fast homework. Oh, it doesn't let me submit because I'm in a preview. Maybe it does. Let's see. See how I did. I know students don't like the multiple choice on here, but they really should be fast. Okay, one variable is missing. Cylinder. Oh, there's 3 types of cylinders. So then the question is, what is that? Is that an ellipse, a hyperbola, or a parabola in 2D? It's an ellipse. They're both squared, and there's a plus. And you can look for it. It should look like an ellipse extended out. Well, there's only one that does that. There's an ellipse extended out. Okay, another cylinder, parabolic cylinder. So let's go to a situation where all 3 variables are present. Okay, so here we have all 3 variables are present. Now let's look at this one, question 6. And notice there's a plus on the other side. So the traces are, if you fix x, what this is saying is actually put in a k there. I know it's kind of funny, but it's saying, in this, later on I go through this in more detail when we get to chapter 14. For now, it's just asking you to do this silly thing. But formally I'm saying, basically, if you forget the x, if you just think it's a number and you just look at the other 2 variables, what do you get? Hyperbola. Same thing if you replace the y with a number minus, and you only focus on the other 2 variables, what do you get? So now if you only look at these 2, they're both squared and there's a minus between them. Hyperbola. Lastly, if you replace z with a constant and you only look at these 2, what do you get? Circles. And then the question would be, well, could you ever get a negative on this side? No, because if you added, in fact, let's move it to the other side just to make it more clear, plus k to the second. This will always be a positive number, in which case we will never have it not make sense. So it will be a hyperboloid of 1 sheet. What if you change the equation to put the negative on the y? It's the same thing, but it's going to be, the graph is rotated about the y-axis, yes. Okay, so these are the things we're talking about. If we change the equation, so we add the 2y, that's going to shift it 1 unit. So if you completed the square, you're going to get y plus 1 squared. So it's 1 unit down. So there are a few little things you might have to think about. But then if you move forward, now we have all 3 variables, but 2 of them are squared. So you'll have that table in front of you, but eventually I want you to be able to just cover up and say, cover this up, parabola, cover this up, parabola, cover this up, ellipse, elliptical paraboloid. So it should look like a paraboloid. Elliptical cylinder, no, elliptical paraboloid. Submit. So I really want the homework to be that fast. This is more of kind of a survey of names. Let's see if we get further down. Here we go. All 3 are squared, and they're all with a plus. It's an ellipsoid. All 3 are squared. There's 1 minus, and this is a plus. So if we did traces, which should be hyperbola, get rid of that circle, get rid of that hyperbola. So it's hyperboloid, and because this is positive, hyperboloid of one sheet. That's what this homework should be like. And then there's a couple questions at the end. The last 3 questions are the challenge. So I hope you can get through the first part. The last 3 questions, you have to translate this the same way we translated a question in the first homework assignment. You have to think about it a little bit, and then after you translate it, you'll have an equation. And then once you have the equation, you can give the name. Give an equation of this, same thing. Translate, write the equation, then give a name. So it's kind of interesting. It gives you these couple scenarios. And then the last one is for you to think about. It's asking you to do a hyperboloid of one sheet. So you're going to write down the general equation of a hyperboloid for one sheet. At some point I'll post about this. This is probably the one that people will get stuck on. But the start of that question is to write a hyperboloid of one sheet. Which one general way to write this is this. B squared minus z squared over c squared equals 1. This is probably the best place to start. And then try to figure out what numbers have to be in these 3 spots to make the following things happen from the story. So I'm going to leave you to kind of think about that. It tells you basically what the radius is. Sorry, I bumped my screen. What a few of the radiuses are of the circles, and from that it's enough information to figure out what those are. But that's meant to be more of a puzzle. The rest of the questions should be fast. All right, hope that helps.